I'm Sam. I work for Sellafield Ltd, where I work as a technical support advisor for the Thorpe reprocessing facility and the inactive tank farm. We're here at the Lakes College to talk about the reactivity series. The reactivity series is a list of metals that are arranged in order of their reactivity. This means that the most reactive metals are at the top of the list and the least reactive metals are at the bottom. The reactivity series is based on the displacement rule, which states that a more reactive metal will displace a less reactive metal from its compounds in a displacement reaction. For example, if we have a piece of zinc metal and we add it to a solution of copper sulfate, the zinc will displace the copper from the copper sulfate solution, forming the zinc sulfate and copper metal. This is because zinc is more reactive than copper according to the reactivity series. So the reactivity series can be used to predict the outcome of other displacement reactions as well. So for example, if we have a piece of iron metal and we add it to a solution of magnesium chloride, no reaction will occur. That's because iron is less reactive than magnesium and can't displace it from its compounds. The reactivity series can also help us predict the vigour of a reaction. The more reactive a metal is, the more vigorous the reaction will be, so the more energetic and potentially more interesting. So in conclusion, the reactivity series is a useful tool in chemistry for predicting which metals will react with other substances. Based on the displacement rule, which states that a more reactive metal will displace a less reactive metal from its compounds in a displacement reaction. The reactivity series can help us predict the outcome of other reactions and the vigour of a reaction. In my work with Thorpe, which is a nuclear fuel reprocessing plant for Sellafield Ltd, one of the things we do is to separate out the heavier metals, like uranium, from fission products, so they can be recycled and the fission products then can get further treatment. The process of this involves adding an organic solvent with special binding components called ligands. These bind to the heavy elements and pull them into the solvent. So once they're in the solvent, some redox reactions occur, so we can separate out the heavy elements from each other so they can be stored appropriately. So where I use my knowledge and understanding of the reactivity series is when we treat the solvent. Since we're separating radioactive elements, the radiation caused the ligand to degrade and form a different ligand. This new ligand can be combined so strongly to the heavy elements, preventing the redox reactions from working effectively, allowing us to separate the different metals. And not being able to separate the heavy elements means they can't be stored and treated properly. So to manage this issue, we routinely treat the solvent with sodium carbonate, so that's Na2CO3, which is aqueous. So because sodium is more reactive, it can displace the heavy metal in the new ligand to form a compound which is then soluble in the aqueous phase. Since the organic solvent and aqueous mixture are immiscible, they don't mix, we can now remove the aqueous solution which holds the new ligand. So we can put the original organic solvent back in and allow the heavy elements to be captured by the correct ligand.
Find inspiring lessons, ideas and planning at developingexperts.com.